2014 Mechanics Level 3 paper, question number 3, and we're looking at translational motion. We've got a system with two discs, A and B, attached together with a light cord. The light cord part just means that there's no mass of the cord. The discs slide across a frictionless surface. We don't have to worry about friction. Disc A has a mass of 0.517 kilograms, disc B a mass of 0.684 kilograms. Disc B is stationary, so velocity equals 0 for disc B, and disc A is moving towards disc B with a speed of 1.21 meters per second. A. Show that the speed of the center of mass, so center of mass of the system, is 0.521 meters per second. Show all your working. Okay, probably the easiest way to do this is to work out the momentum of the system, and then divide by the total mass of the system, because that's going to give you the velocity of the system, which has to be the velocity of the center of mass. And in case you didn't catch that, that's our P equals mv momentum equation rearranged. Which equals the center of mass. Yep, give it a go. There's other ways you can do this as well. There's more complex, convoluted ways. You can like work out a position, then 1 second later where for A, and then position 1 second later where A will be if B is stationary, and find the center of mass between the first two positions, wherever that is, and then between the second two positions, wherever that is. Work out the distance gone from there and the time that it took, which you said is 1. But it's much easier just to do it this way, I think, down the bottom. Okay. B. The discs collide, of course. After the collision, they're moving at right angles to each other, which also makes for a very nice triangle when we're dealing with vectors, so we're likely to have to do a vector thingy here. Disc A receives an impulse of 0.250 Newton seconds. Okay, so that's our change in momentum equals F change in time. So the change in momentum is 0.250 Newton seconds. That's for A, but it's also got to be the impulse for B, because it's the same force. Every reaction is an equal and opposite reaction force, and the same time for the collision. So part 1 is show that the speed of disc B after the collision is 0.365 meters per second. Speed, we were talking about vectors before, but speed is a non-vector quantity, so we don't have to worry about that. We know that the initial velocity was 0, so any change in speed is going to be equal to the change in momentum divided by the mass. So very nicely here, we can just take that change in momentum and divide it by the mass of B. Was it B that we were working out? Yeah, 0.684. And then that'll give you your answer. When you're explaining your reasoning, you would be explaining that the change in momentum for B is the same as for A, therefore you can use that to calculate it. Okay, carrying on. Part 2, determine the size of the momentum of disc A after the collision. Ooh. So this is where we're getting into some vector calculations here. Momentum must be conserved. So the change in momentum for A has to be the final momentum of A minus the initial momentum of A. Excuse me. So we're actually trying to find the final momentum of A, but the vector calculation, the vector equation we use is still going to be the same. So we know this, the initial momentum, and we know what this is, the change in momentum of A, because we're told what it is up above. It's just a matter of finding all of the angles and working that out. Now we might strike a bit of a problem here. Let's just scroll back up, because, excuse me, I'm not feeling too well. It might strike a bit of a problem because we don't know where, like A was, train, pause. Okay, carrying on. It's the benefit of living next to a railway track. So as I said, we might have a bit of a problem because we don't seem to have a reference point. Initially, you had A coming in like this, and then there's that collision, and then A has gone off on that angle and B has gone off on that angle. We don't have a reference point to that initial position, which is something that we would need. However, we can talk about this a little bit further, and we might be able to come up with a different way of working it through. That if we stick with the total momentum, initially was equal to the momentum of A, but then the momentum after, total momentum, which is still the same, and has to be equal to that initial A moving to the right. That total momentum afterwards is going to be the momentum of A plus the momentum of B. And we've been told the change of momentum of A, which we might be able to, well, again, we're still stuck with that same problem, but let's just go and have a look. So we've got if we were just using this diagram as a reference, that would be more than enough, I think. But for the momentum of A, perhaps since we don't have an angle, we can just sort of estimate, I don't know, based on the direction that we've got here. So if B is going off in this direction, that's trying to copy the diagram from above, and the total momentum of those two added together has to be equal to the total momentum that you had initially, which was the momentum of A initially. Then what does that tell us actually? I think I'm missing something. That the change in momentum of A is actually the momentum of B, which we know because it's just given to us as a speed and a velocity. I freely admit that I'm fluffing around a little bit here because I'm not totally 100% sure. I might have to come back with a little addition and an update to this video, otherwise we're going to get a little bit long. But I think you've got enough perhaps to go on if you use those original reference points from the diagram and do the calculation. I'll have a little think about it. I might add a final little video to redo that one. But anyway, let's move on. The discs continue to slide until the cord is fully extended. When this happens, both discs change their speed and direction. So this is again a different, like a third situation of a collision-y type thing. But carrying on, by considering the forces that act on the discs, explain why the momentum of the system must be conserved. Okay, so when we're talking about considering the forces, there are no external forces acting, because the force acting on one acts on the other one through the tension of the cord, and because there are no external forces acting, you're not changing the momentum of the system. So if they're all internal, then it's just a shift in momentum within the inside of the system, you could say. That really covers it, I guess. But is there another question? No, that's it. So I'll have another look at that other question and then bring it back to see if I could do any corrections. Okay, just had a quick look and I can take it on to the end of this with this tricky question. The size of the momentum of disc A after the collision. Just refresh your memory, go back if you're not sure, pause and rewind the video about what the situation was, but it was on the right track, and the trick here is that they're actually not interested in the angle. So if you're asking for the momentum, it's a little bit, I'll just say it's a little bit, maybe, if I'm being, I don't even think I'm being pedantic. Okay, I'll just say it. I think it's a bad question, because when you're asking to find the size of the momentum, especially when you learn about vectors at level 2, and this is a level 3 question, you'd be expected to find the angle. So you could find the angle now once you've got the final values, but the solution doesn't actually go there, which is interesting. So it's purely Pythagoras, using the momentum of A plus the momentum of B. and that was told as the change of momentum of A, which is what it is. And then this was the momentum of A initially. So the momentum of A initially should be the sum of the momentum of A afterwards and the momentum of B, since momentum of B had 0 to start with. Maybe it's not a bad question then, okay. But it's a bit unusual that the solutions don't expect theta. And maybe to be just a little bit pedantic in the answers, you should go to theta on this. But you're basically drawing your diagram over the top of their diagram. And we know that's a right angle there, and then once we work out the lengths of the sides, then we can work out all of the angles and the reference points. But yeah, anyway, there you go.